Hi everyone. Today we'll talk about three major theorems about continuous functions. To help us understand the first theorem, I have an exercise for us. We are given four functions and we must match them to their graphs. If you would like to try this exercise on your own first, you can download these notes using the link in the video description. I believe that the function e to the power of x corresponds to the second graph because it grows rapidly on the right side of the y-axis. The function square root of x is not defined for negative x's, so it must correspond to the third graph. The function 1 over x is not defined at x equal to 0, so it must correspond to the fourth graph. By the process of elimination, absolute value of x must correspond to the first graph. These four functions are famous. I am certain you have seen them before. Let's take a look at the first two graphs, absolute value of x and e to the power of x. Both of these functions are continuous everywhere. The function square root of x is not defined for negative x's, but for x's bigger or equal to 0, this function is defined and continuous. So you could say that the function square root of x is continuous on its domain. The function 1 over x is not continuous at x equal to 0, but it is continuous at any other x. So again, you could say that the function 1 over x is continuous on its domain. These facts about continuity of these four functions can be extended to other famous functions you know. The first theorem says that famous functions such as polynomials, absolute value of x, e to the x, sine of x, and cosine of x are continuous everywhere. Root functions 1 over x, natural log of x, and tangent of x are continuous on their domains. You have already seen the graphs of absolute value of x, e to the x, square root of x, and 1 over x. Let me show you a few other examples. Here, you have first a graph of a polynomial. That function is continuous. The graph of sine of x also suggests that sine of x is continuous. Natural log of x is not defined for negative x's or 0, but for x's where it is defined, which is for x is bigger than 0, this function is continuous. The function tangent of x is not defined for multiples of pi over 2. But for any other x, this function is defined and continuous. There was something special about the first function x to the third power minus x plus 1. This function really consists of three functions, x to the third power, x, and 1. Individually, these three functions are continuous. Then we added them or subtracted them, and we still obtained a continuous function. This is true for other continuous functions as well. This is the statement of the next theorem. If you have two functions, f and g, both of them continuous at a, then if you add them or subtract them or multiply them or divide them, you will still get a continuous function. In the last case, assuming that g of a is not 0, so you avoid division by 0. If you create a composition of the two functions, f of g of x, you will still get a continuous function, assuming that f is also continuous at g of a. Let's see if we understand this theorem by completing a problem. We are given a function, f of x. We must determine where this function is continuous. If you would like to try this exercise on your own first, this is a good time to stop the video. This function consists of three functions combined, ln of x, square root of x minus 1, and x squared minus 4. Individually, each one of those functions is continuous on their domain. Let's see what those domains are. For example, the function ln of x is continuous and defined only for x is bigger than 0. So it is defined on the interval from 0 to infinity, where 0 is not included in the interval. To keep track of axes for which this function is defined and continuous, I will draw the x-axis. I will now add x equal to 0 to it, and I know that for x is bigger than 0, the function ln of x is continuous. The function square root of x minus 1 is defined and continuous as long as whatever is inside of the square root is bigger or equal to 0. So I know that x minus 1 must be bigger or equal to 0, which is the same thing as saying that x must be bigger or equal to 1. So square root of x minus 1 is defined and continuous for x's bigger than 1. I used brackets here to denote the fact that this function is defined at x equal to 1. Let me add this condition to the x-axis. I add x equal to 1 to my x-axis, and I know that I can use any x bigger or equal to 1. The function x squared minus 4 is a polynomial, so it is continuous everywhere. However, x squared minus 4 is in the denominator, and we must ensure that the denominator is not 0. And unfortunately, this denominator is 0 for two x's, x equal to negative 2 and x equal to 2. So I must exclude those two x's. I must say that x cannot be negative 2 and x cannot be 2. Let me add those 2 points to my x-axis, negative 2 and 2, and add open dots around them to remind myself that these 2 points are not included. So what are the x's that satisfy all those 3 conditions? Well, these are the x's that are bigger or equal to 1, not including the 2. So as long as x is in the interval from 1 to 2, 2 not included, and the interval from 2 to infinity, this function will be continuous. I have one more theorem for us. The theorem below I like to call you can move limits inside continuous functions. Imagine you have a function f of x that's continuous, and you also know that the limit of g of x exists at x equal to a. Then, when you take the limit of the composition of the two functions, you can take the words limit and move them inside of the continuous function f. That's exactly what happened here. To understand this theorem better, let me show you a few examples. Below, we need to find the limit as x approaches 2 of square root of x to the third power minus 1. Well, square root function is continuous on its domain. So what I'm going to do, according to the theorem above, I'm allowed to take this limit and move it inside of the continuous function square root. So I know that this expression equals square root of the limit as x goes to 2 of x to the third power minus 1. To compute the limit inside of the square root, I simply use the direct substitution property. This is a polynomial. I plug in 2 to this expression, I get 7, so I get square root of 7. You could say that I would have obtained the same answer if I simply plugged in 2 to this expression. And indeed, sometimes this theorem will tell you that you can simply plug in the number to the given expression. However, it will not always be the case. Take a look at the next example. This time, we must compute the limit as x approaches 3 of this expression. Note that this time I cannot simply plug in 3, because if I did so, I get the indeterminate form of 0 divided by 0. Instead, I apply the theorem above, and I take the limit, and I move it inside of the continuous function sine. And I get sine of the limit as x goes to 3 of x squared minus 9 divided by x minus 3. To compute the limit inside, I apply algebraic manipulations. I factor the numerator, and I get the sine of the limit as x goes to 3 of x minus 3x plus 3 divided by x minus 3. Now, x minus 3 in the numerator and in the denominator, they divide out, which leaves me with sine of the limit of x plus 3. Now nothing is stopping me from plugging 3 to that polynomial, and I get sine of 6, which is my final answer.